Let us discuss this example. Okay, so we have a set A which is a subset of R2 in a Euclidean metric. So we have to prove that it is an open set. So you remember the technique of proving set is an open. We take any arbitrary point and we find radius R such that open ball around P should lie entirely inside set A. Okay, so let us start to do. I will write the given set first. We have what we have. A is equal to, let me write it once again, xy belongs to R2 such that x is positive and y is also positive. So if I draw a diagram, it will be like this. This is y axis, this one is x axis, you know that, y axis, and this one is x axis. So in first quadrant only we have both of them are positive. So that means given region is nothing but first quadrant. Okay, so we have to prove that this first quadrant is an open set. See, I will select any arbitrary point. I will clearly mention here to prove that A is an open set. Okay, how to prove set is open? This first quadrant is nothing but set A. So to prove that A is an open set, so I will take any arbitrary point. Let P be is equal to P1 comma P2, since it is in R2, belongs to A, be any arbitrary point. Be any arbitrary point. See, that means what I am doing, I am selecting one point P, having coordinates P1 and P2. So that means I am selecting a point P of first quadrant. So implies obviously P1 is positive and P2 is also positive since it is in first quadrant. Okay, so I will call it as inequalities number 1. Okay, see, let what I am doing, R is equal to minimum of P1 comma P2. See, what will be the P1 if you draw lines like this? So this is our P1 and this is our P2. This distance is our P1 and this distance is our P2. So my target is to draw an open ball around P which will entirely lie inside a set. That means we should entirely lie in first quadrant only. Get it? So in the diagram you can easily see what is a minimum value. Minimum value is P1, so that will be my R. Okay, but it is not fixed. No, if your point P is here, in that case P2 can be minimum. So point can be anywhere. So what is my purpose? I'm selecting a minimum radius. Okay, whatever the minimum of these two values, that will be my R. Clearly R greater than 0. Clearly R. See, both of them are positive, so that's why their minimum will be positive. See, what is my claim now? So my claim means this thing I am going to prove. My claim is B P comma R subset of A. See, I am going to prove that if you consider a ball with center P and radius R, if you draw ball like this, open ball, then it will entirely lies inside set A. So this thing we have to prove. In diagram we can easily understand, getting, but we have to prove it mathematically. So that means simply we have to prove that this set is subset of that one. How to say prove that one set is subset of other? We select any arbitrary point from first set and we try to prove that element in second set. Okay, so I am going to do the same. So let x is equal to x1 comma x2 belongs to B, P, R. So that means I have selected one point x. I don't know where it is. Suppose point x is here. So x belongs to this ball. I will prove that this point is in A. So that's why this set is subset of this one. So this is a simple thing we have. So see, x belongs to this open ball. That means if any point lies inside a ball, that means distance of that point from the origin is less than R. So that's why distance of x from P is less than its radius, right? But this is a Euclidean distance, so that's why we write in terms of norm x minus P is less than R. Okay, implies x means what? X means x1 comma x2, p means what? P1 comma p2, p1 comma p2 less than r. Okay, implies you know that we need to subtract component wise. That means x1 minus p1 and x2 minus p2, no space we have, so I'm writing this is less than r. Okay, you can make a screenshot of it. After that we will go further. Please make a screenshot of it. Let us continue. Let us apply the definition of norm. So by definition of norm, what can I write? Implies. By definition of norm, norm says this is square root of first x1 minus p1 square plus square of second x2 minus p2 square less than r. Right. So now I will, to remove a square root, I will take square of both sides. So therefore x1 minus p1 square plus x2 minus p2 square less than r square. See, sum of these two numbers, positive numbers, it's great less than r square. So that's why each of them is also less than r square. So that's why x1 minus p1 square less than r square and x2 minus p2 square less than r square. So you know the next step. What is our next step? I will take square root of both sides. So this is mod x minus p1 less than r, and here also I will take square root of both sides, mod x2 minus p2, here x1 less than r. See, but you remember the definition of r. R is minimum of p1 and p2. You are getting? R is minimum of p1 and p2. So therefore r is less than or equal to p1 and r is less than or equal to p2. We will have equality, no doubt, but either these two are equal or these two are equal. Getting? So that's why we have actually this relation, less than or equal to. So therefore, see what we are getting? Mod of this one is less than r and r is less than p1. So that's why mod x1 minus p1 less than p1. Right? A less than b, b less than c. Simple logic I applied. Here also I can apply the same logic. That means mod x2 minus p2 less than r and r is less than p2, less than or equal to. So that's why we will have less than p2. I will remove it. It is not required now. Okay, it is not required. See, you know that result mod a less than b if and only if minus b less than a less than b. In FY BSc we have studied this result, right? So this result I am going to apply here. So therefore minus p1 less than x1 minus p1 less than p1, and for that also I can apply the same result. Minus p2 less than x2 minus p2 less than p2, right? So this less than p1 is not required. So simply I write minus p1 less than x1 minus p1, and here also I will do the same, minus p2 less than x2 minus p2. That thing is not required. Getting? So I am going to add p1. What will happen if you add p1? If you add p1, minus p1 plus p1 will be cancel and 0, and if you add p1 we will have x1 only. Here I will add p2 on both sides, so therefore 0 less than x2. Getting? That means x1 is positive, x2 is also positive, both of them are positive. That means therefore the point x having coordinates x1 and x2, this is member of A. Since A has the same condition, A has the same condition, if both components are positive, so here we have proved both components are positive. Let me remove it. It is not required now. So x belongs to A. Okay, the set A. So we had taken x from this ball and we proved that x lies in A. So therefore we can declare, open ball BXR is subset of A. Sorry, there was not x, there was P. BPR subset of A. So that means we had set A, we took any arbitrary point P, and after that around the point P, we could found open ball which entirely lies inside set A. So therefore, we can declare set A is an open set. So therefore, A is an open set. In this way we proved. You can make a screenshot of it, and after that we'll stop. Thank you. Bye bye.